So we have two pieces, training and testing. Sometimes the third piece, we call it tuning, or say validation. Tuning the parameters right after your training and the testing, then you tune it. There's the three pieces. So sometimes you just measure, okay, all I do is count. If misclassified something, I call it an error. If I succeeded to classify something based on the label, I say, okay, it's successful. And then you say, hey, I have 75 successful, 25 for mistakes, then you claim 75% of error. That does not tell much. It really depends on a lot of other questions. How big is your testing data? How you sample your test data? How much similarity your test data with your training data? There's too many questions you have to answer to argue. Say you have this much accuracy. Now, a simple error is this: resubstitution error. If you simply make your training data, put it back into the test, and then you get a very good result. Sometimes it's even 100% right. But this is called a hopeless optimistic. That means you can do mistake. Okay. So the first baseline is whenever you do data mining, we call it the supervised classification. You get your data carefully labeled or come from other result, and then you split in two pieces. One, I call it training data. Another one, I call it testing data. They could be significantly different. For example, when you do the real estate evaluation, you can use the data from one town to do the training, and they get the data from another similar town to do the testing. They are separate, different data, but they share the same kind of attributes, like the square picture, the footage, and the structure, material, Another thing is tuning. A lot of times, in the training process, you have two stages. And you got to build the basic structure. This is the training. And you can come back to optimize the parameter setting. Give you an example. The decision tree. During the training period, you might make it all the way to the 100%, and then you have a problem of overfitting. The overfitting will not be found until you do the testing. Well, after you finish the testing, you say, well, oops, that's just bad. I have 100% accuracy. Why suddenly become only 30% of accuracy? And then you have a problem of the overfitting. So you come back, use the other set to do the tuning, and they say, kind of how much you have to print off. And then you say, well, be better. You come back into the test again. Remember that. These three sets need to be independent. If they are not independent, it's not going to help. Let's say you did the training and the testing, you found that there are too much difference, and you come back to do the tuning by using the training data again, you won't do any help. Because this training data already perfect fit, right? Are you with me? Simple things like that. So, in many times you have three sets: training data, tuning data, or some validation data, and the test data. But that's when you have enough data for you to split into three pieces. Think about our weather example. We totally have 14 instances. And if you split the 14 into three sets, you got trouble. Each one is just a few, even not cover all the classes, right? The key we're going to learn today is how to make the most of the data. You have big data, you have small data, you have noise data, you get all different data. And based on the characteristic of the data, you need to make a decision. That decision is a unique human decision based on your understanding of this course. Unfortunately, I only put 1 hour, and even the book from the textbook does not cover this. This is from the Wake book. It's very good. So there's 3 basic approach. The baseline approach is called the hold out. And the hold out means typically you put 2/3 for training and 1/3 for testing. But this one assumption is both the training sets and the test sets need to be large enough. For example, for the weather example, if you split in 2/3 for training, then you get about 10 for training, 4 for testing. 1 out of the 4 mistake, you have 25% of error. If we have 2 in the testing data, you get 50% of error. Can you see it? You cannot do that. So we have some. What the P mean here? If n is 1,000 times, you get 750 times the success, then you estimate 75%. That's common sense. That's okay. But now, here's the question. How close is this to the true successful rate, P? Now, your sampling is 1,000. Let's say you're talking about the infinite population. That's all statistics assume. If it need to be a science, it need to be infinite population. Now you sampled it, only 1,000. The implication is you most likely, in 80% of confidence, it's going to be this real successful rate is between 73.2 to 76.7. What does that mean? I taught statistics. After I finished the course, I found that only a few people understand what that really means. Okay, explain in English. Only a few people. I have to honestly explain to you. When I was in the undergraduate, I finished my statistics class. I found this B or C. I know it's bad. I never understood what that means. Now, let me try to explain to you what that means. That means if you have infinite many of those populations, you keep sampling each time you sample thousands of the experiment. Each time you do 1,000. And you keep doing, and you are going to find that 80% of the time, your success rate is around here. That's what it means. It's a little bit abstract, I know, but that's exactly what it means. And if you do only 100, that means now you see this is spread bigger from 69.1 to 80.1. That means you have more deviation, right? Because your sample size is smaller. Now, this is the Bernoulli trial. And remember, if you do 1 time, your mean is P. This is your standard deviation. But if you keep this n bigger, now look at the random variable of the success over the total number of experiments. And then the variance divided by n. Can you see that? And the more you do, the more you're going to get the accurate. Narrow it down. That's the function. And when we talk, the probability, you always have to talk on that. Z-value. That's the Z-value. Last time you remember I talked about how do you compare apple with orange. Well, if I want to compare the size, I can. I say here is an average apple. This is an outstanding origin. Okay, how do you say average? You always have the mean here. And you always compare with the standard deviation. That means you're going to make this normal distribution and figure out the z value. Means you're going to, in any population, shrink it and morphing into exactly like the standard deviation by divide the deviation and the shift to the mean. Just a little two operation because you only have two parameters, right? Once you do this, you understand what this means. That means from here, negative 1.65, that's 1.65 deviation to the left, 1.65 deviation to the right. For this interval, covered 90% of probability. That's what it means. So we look at this table. And then what you claim is what is the probability your real expected successful rate is between that interval. You can only answer that. You cannot answer, it's a joke. There's a student that made a statistical assumption and no assumption that tried to show two populations have a significant difference. In the statistical result, after finished the analysis, they found the right inside of this 95% of confidence interval. That means there's no way to decline the no assumption. They said, can I change the assumption, say they are equal? And then I'm going to prove it. Statistics cannot prove anything equal. It's just they just say by how much confidence you know that cannot be the same. So that's what it means. So when you, now here's the application. Figure out what is the difference between the probability and the statistics. What you learn, the probability is the theory. The theory comes from an assumption. If I know this p, which is the real mean value, and then I know this population, if I draw out, continuously draw out this many, how much possibility I get this? That's the probability. But the statistic is the reverse. You really don't know, in reality, you don't know what's the real successful rate. You really don't know if this coin is biased or not biased. You don't know. The only thing you know is you're going to draw a sample size, like 100 or 1,000. And then you're going to find this F. You find this your result because you are sampling. Once you find this F, you are doing the reverse operation based on the probability, what confidence level you want. Let's say I want the 90% of the confidence level, then your Z will be 1.65. Based on this Z and your F, you're going to find the P. That's what you show. That's how we calculate the P. The P is something in the bucket. You really don't know. What you know is what you sampling from the bucket, and you find the F. From the F, you can know the probability. The P should be